Good day everyone, this video is an experimental project, part of a series of videos about controlling brushed DC motors under no load conditions. Here we need to design a PID controller implemented in Arduino Uno in order to maintain or control a constant angular speed of 200 RPM with an overshoot of less than 10% and a settling time roughly in a couple of seconds. In the past videos, we did introduce the digital control systems. We talked about the user requirements with some definitions, such as the rise time, settling time, overshoot. We also had dedicated videos on both on how to derive the mathematical model for a DC motor and about the encoders and how they work. In this video, we need to find the experimental PID solution to control the speed of the motor within a specific user requirements mentioned. To do this, we need to use the Arduino Uno and a H-bridge, the L298, and a 6-volt motor for this case, with a maximum angular speed of around 300 RPM. As we may know that we need to have a user input. The user will be setting the desired input angular speed of 200 RPM. Now, since we are setting the input in the Arduino itself, so there's no need for any external devices, and a more simplified block diagram may look like this. This is our zero old or our PWM in our case. This is our motor and the encoder. Perhaps this is the pulse counter or another sampler here. If you notice that most of the activities happening all the way before the motor driver is all included in the Arduino. So our Arduino actually is the one which is enclosed in the dashed square. If you needed more information about how this Hall effect based encoder works, please do check the previous videos we have for both the encoder, and if you are interested in the mathematical model for the motor, the theoretical implementation of both the mechanical and the electrical equation, check our previous videos as well. As you may know, there is more than one approach to designing a controller for a plant or the motor in our case. Because the motor or our plant, together with the driver, they are both in the continuous domain, we will leave the motor transfer function in the S domain and simply just implement the controller in the Z domain, or the discrete form, in terms of difference equations. So as described as well in the previous video, now the input for the H bridge or the motor driver will be a square wave, okay, of a series of voltage pulses, square waves, and the output of the motor will be actually the encoder resembling the number of rotations. So the duty cycle of the square wave as the input for the H bridge is the main control signal for the motor overall voltage. The duty cycle will dictate what voltage that's gonna receive, and as a result we will be able to control the motor in order to maintain our constant angular speed of 200 rpm. Now the feedback information is given by the encoder via a series of pulses from two Hall effect sensor, and we will be able to even determine whether the motor is going in counterclockwise or clockwise direction. We will be able as well to determine from the speed of the pulses the angular speed of the motor, and hence we use this information back to the Arduino in order to improve the PWM duty cycle, which will be fed to the motor again in order to keep or maintain the desired angular speed. If you needed to do more in detailed analysis in MATLAB for the motor in both, for example, open loop or closed loop configurations, you need the mathematical model for the motor together with that of the H bridge. I will show you how to do this experimentally later in the video. But for now, it's very important to find the number of pulses per revolution, as this will help us calculate the motor angular speed in Arduino. We have to use that information as a feedback to the Arduino. The number of pulses is normally the number of signals generated by the Hall effect multiplied by the gearing ratio of the motor, and that will tell you the real round per minute of the motor. It's recommended you find this out using the datasheet, but it's also, I recommend you double check this experimentally as well, especially if you are in doubt about the motor part number or you are expecting it has the wrong label on it. So the best way to find out the encoder pulses per revolution is to run the Arduino code that counts just the encoder pulses while rotating the motor by one revolution. You can do this by hand multiple times and take the average of this. This is the Arduino code I downloaded on the Arduino. It works out the number of pulses as you rotate the motor. I know from the datasheet that this motor has around a gearing ratio of around 78, and the Hall effect generating 11 pulses. So 11 times 78, this is gonna give me something around 858 or 860 pulses per one revolution. So rotating now the motor by hand, we should get something close to this number. Let us now go over the wiring diagram of the hardware, how the Arduino, the driver, and the motor, together with the encoder, are all connected together. Let us start first with the power supplies. Now, this motor is a 6-volt motor, so obviously all motors, they draw currents higher than what Arduino can provide. So for this, we need an external power supply, and we could connect this to a voltage, and that is the ground. That voltage is going to supply the motor with. Now, for our purpose, we're gonna supply this by an 8 volts because we have a 2 voltage drop across the H bridge. So 8 volt, if you supply 8 volt, you're gonna get an output of 6 volts for the motor. For this type of brush DC motor, it's okay if you wire the red one to the negative one, because that's going to affect your direction, which is in any way controlled by the 2 pins which are here. Since we are talking about the motor direction, we can connect now the 2 direction pins from the motor driver to Arduino. We're going to use the gray, so that's 1. We're going to connect it to pin 4. And we can connect the other one to pin 5. So that's 5. This is 4. We will be controlling the motor speed by the PWM output. So that's going to be pin 6. Now let's wire the power supply for the encoder. And 3.3 volt. And we also need to supply the encoder output to Arduino to pin 2 and 3. and that's to pin 3. So this is it. Just make sure that the 8 volt is supplied by an external power supply that is capable of delivering the needed current. In our case, just one motor, so we are expecting maybe 250 milliamp will be sufficient. Check the data sheet always to make sure that you are supplying the motor with the sufficient current. And the reason we put 8 volt, as we mentioned before, because there is a 2 voltage drop across the motor driver. So in order for us to get a 6 volt over here, in order to get a 6 volt, we need to get the motor driver supplied by 8 volt. One more thing you should do is you have to put the grounds together. So this is an external power supply, and it's important you connect the ground for the external power supply with the ground of that of Arduino. So maybe we could just simply connect them from here at some point. Okay, and that's it. Here I'm assuming that the Arduino Uno is powered by your USB cable. Okay, so this is going to your PC. It would be interesting to see the open loop performance of this hardware first, i.e. without implementing any controller in the Arduino. This can be done by, first we can input the 200 RPM value as a user input, and inside Arduino we convert this to a voltage equivalent that will be fed to the motor driver via pin number 6. So that voltage is going to be fed in square wave to the H bridge, which will in turn activate the motor with the voltage corresponding to the 200 RPM. The encoders here in the open loop configuration will be only used to display the RPM on the screen, and they will not take any part in the control. Now, downloading the open loop code onto the Arduino Uno, now turning on the power supply, external power supply to the motor, you will see that the blue line is the set input angular speed of 200 RPM, and the response of the motor in the open loop configuration is shown in red. Obviously, the response is not following the input at all because we don't have any controller involved, and it's kind of blind control, if you wish. So we have just seen the open loop response for the motor at a certain user input. So at 200 RPM, we have simply calculated the voltage based on the datasheet. So we know that the maximum RPM is 300, and that's equivalent to 6 volt. So based on the 200, we supplied a pulse width modulated signal representing the 4 volts. And we have the results on the Arduino serial plotter. However, now, if we need to apply the closed loop configuration, we have to design the controller and the encoder output will not be only used for simply calculating the RPM, but we will be using those information in order to calculate the error between the obtained RPM and the user input RPM. So in the closed loop configuration, we are expecting a PID controller to be implemented in Arduino Uno. So if we assume that this is our controller, and this is our zero order hold, or the PWM generator. This is our H bridge. And this is our motor with a connected encoder at the end. This is our comparator, and this is the user input, which is already implemented inside Arduino. Now, an important thing to keep in mind that the RPM calculated here from the encoder is compared with the input RPM, and the subtraction of those is what we have the error signal in the time domain. If you recall, in the Laplace domain, the controller will have this form. It will have a proportional component plus an integral component, Ki over S, plus the differential component, Kd times S. And the error signal is E of S. So in order to obtain the output here, say this is the A of S, this is equals to the error multiplied by the controller. However, since we are dealing with an Arduino Uno or any computer-based hardware, we won't be able to use the Laplace. We have to use the discrete or the difference equations. So what do we need to do now is to implement this as a difference equation inside Arduino Uno. Now, converting the output of the controller into a discrete time domain, we're going to get something like this. So that's capital A of S will be A n of sampling time multiplied by the error signal Now the integral part can be written as such. Where capital T is the sampling time. Now this conversion to the difference equation format is done by multiple methods. For example, the integrator term Ki over S is written as such in the discrete time domain using the trapezoidal rule approximation. So you can have a read about this method. You will see how this is done. As for the differential component, you need to have a look at the backward Euler approximation. So the Euler approximation method is used to write the differential component in the difference equation format. So in the open loop configuration that we have already done before, we didn't have any controller involved. All what we were doing was simply having the controller replaced by a simple RPM to voltage relation based on the datasheet. And the output of the PWM is always constant, and the motor is being driven at a certain RPM. And we were only displaying the encoder response on the screen. There was no feedback and there was no subtraction at all. So that was the open loop configuration. Whereas here now, we will implement the controller. Here we have to use the encoder information and subtract it from the user input to obtain the error. Now we always need to maintain the error to 0 as much as possible via the help of the controller. Now implementing this difference equation in Arduino Uno will allow us always to output a PWM that is suitable to control the motor and bring the output RPM of the motor equal to the user input. It will try its best, but of course this will depend on your parameter, the Kp, the integral 1 Ki, and the differential component Kd. So in our Arduino program here, we will use the trial and error method just to optimize those parameters in order to achieve our objective. Our objective is to maintain a 200 RPM as input by the user. After implementing the difference equation in Arduino Uno, we will try to find the optimal values for Kp, Ki, and Kd. There are multiple methods available. The first one is the trial and error method, which we will be using here. There are other techniques like the curve techniques or the Ziegler-Nichols method. However, in our work here today, we will simply do the trial and error method. The way the trial and error method works, first we set the integral and the derivative terms to 0, and we pick an arbitrary value of Kp and check the response. We have to make sure that we are almost getting what we would like to get, and after this we start tuning the Ki and the Kd values until the system reaches the required or the desired oscillatory behavior. So normally we start with the Kp, and then once it starts reaching our desired value, we may get oscillations. We adjust the Ki term so that the oscillations reduce or stop. Then we adjust the Kd parameter in order to get a faster response. Let's first download this code on Arduino Uno with a Kp of 0.01 and setting the integral and the derivative terms to zeros. Okay, I will turn on the power supply and check how it will perform. Obviously, the current proportional controller value is small. We have to increase this. We probably multiply it by 2. Okay, we have to increase the proportional gain in order to reach our desired 200 RPM. it needs a bit more. A bit more. We need a slight increase as well to the proportional term. A bit more. Let's increase this to 0.09. So we will be reducing the proportional constant a little bit. And repeat. Okay, the overshoot is still high, so roughly around 20%. We need to bring it back below 10. This seems to be a better value. If you are now interested in making the response faster, you can adjust the derivative term. Well, this seems to be a kind of an acceptable response based on the user requirements. An overshoot of less than 10%. This value here is around 210 RPM, if not less. So that's gonna make the overshoot less than 10%. As for the response time, you could analyze this further by zooming in into your graph, or you could analyze it in MATLAB or Excel as well. As far as the requirements for this basic video, we just demonstrated how you implement a PID controller in a real application for a brush DC motor under no load conditions. Of course, this is going to vary if you have a load, and if the load is varying as well, that's going to affect your optimization techniques.